Welcome back, everybody. This is our video solution to problem 3 from quiz 4. It's another partial fraction related problem. This time, we're actually going to go through and find a partial fraction decomposition for a given function. So here, our numerator, some linear piece, 4s plus 7. The denominator is 2 linear pieces, so we get a quadratic in total. So it will make sense to do this. And let's just immediately jump in and notice, what should our partial fraction decomposition look like? Well, there are these two linear pieces on the bottom. They're not repeated, so it's actually a very simple partition here. One of these fractions will have s plus 2. The other one will have s plus 1. The numerators have to be degrees smaller than the denominators. Well, okay, these are linear, so we have to just have constants on the top, and we'll give names a and b to those. So I'm going to go through this twice. The first time using sort of the long form method, but not the long form method. And then the second time using the short method. I sometimes call it the thumb method. It's also traditionally known as the Heaviside method. But let's start with method 1. So this is the hard algebra method. So what I'm going to do is multiply through by the denominator of the original function. So I'm going to multiply through by s plus 2 times s plus 1. So multiply by s plus 2 times s plus 1. So when I do that, it's going to clear away all the denominators. So I'm going to be left with 4s plus 7 on the left. And on the right, well, let's see, I have a. And since I'm dividing by s plus 2 and multiplying by s plus 2, those will go away. I'm just left with multiplying by s plus 1. Okay, then the second summand has a b, and just like with the first, the s plus 1 this time is going to cancel, and we'll be left with an s plus 2. Now, one can reasonably easily distribute all this. I tend not to want to do that, particularly when the degrees of things get higher or there's more terms. It just takes a lot of time, and often a lot of that time is wasted, and it's easy to make some mistakes as you go. So I'm just going to leave it in this form and just ask, okay, what are the things I need? So first, I'm trying to find the a and the b, and so what I could do is just ask, well, how many s's do I have? On the left, I have 4 s's. Right? So let's look at the s's. I have 4 s's on the left. And how many do I have on the right? Well, I'm going to get an a times an s and a b times an s. So in total, I have a plus b s's on the right. Okay, so we know that a and b are going to add up to 4. Okay, now how about the constants, right? Well, on the left-hand side, I have this constant 7. On the right-hand side, I'll get constants by doing a times 1 and b times 2. So in total, I have a plus 2b constants. Okay, so now I just need to solve for a and b using this really nice linear system, 2 equations, 2 unknowns. And I could subtract one from another, but man, I just noticed here, like the difference between these two is just I've added a b, right, on the right. That's the only difference. And over here, I've added 3. So b must be 3, right? You've added 3 over here, you've added b over there, they must be the same. So this tells you b is equal to 3. And once I know b is 3, well, what do I have to add to 3 to get to 4? Oh, right, a is 1. Okay, cool. So that's not too shabby. Okay, and so this tells me then that I can go back up here and replace my a with a 1 and my b with a 3. And there's my partial fraction decomposition. Okay, that actually wasn't so horrible, right? I mean, there's some distributivity going on. All right, there's a little bit. I mean, this was maybe a little lucky, right, that we could see how quickly we could get b, but it wasn't so bad. But there's maybe a slightly faster way to do this here. So method 2. Well, I'm going to do this actually also sort of in 2 pieces. So the first time, I'm going to do it again in the long form, and then the second time I'll show you how I actually do it. So let me erase the 1 and the 3 here. Let's pretend we don't know what they are. So we still have an a and a b. And we could copy over this statement. Okay, so we put that over here. And oh, I didn't want to like completely get rid of it over there. So let's just copy it over. Oops. We'll move this back over a bit. Oops. Okay. So when I get to this step, another approach I could take is to start plugging in specific values of s. So for example, if I'm trying to get the s plus 2 coefficient, well, okay, what if I made s equal to -2? If I make s equal to -2, then this second summand is going to go away, and I'm just going to be left with something times a. So on the left-hand side, when s is -2, I get 4 times -2, which is -8, plus 7 is -1. And on the right-hand side, okay, -2 plus 1 is -1 times a. So -a is -1, and so a is equal to 1. Now, if I want to get the b, I just make s equal to -1, because that's going to kill this summand with the a. So when s is -1, I'm going to get 4 times -1, which is -4, plus 7, which is 3, equals, okay, again, this summand goes away, and -1 plus 2 is 1, so 1 times b. Hey, we have a equals 1, and we have b equals 3. So that's pretty cool. Now, all we did in this method, right, was evaluate this equation when s was -2 and s is -1, and that allowed us to get an a and a b. And what I claim is that we could have done this right from the start. We didn't need to actually write down this this modified form, right, where we multiplied through by s plus 2 and s plus 1, which itself might lead to some errors. Instead, what I want to do is go back up to this original equation and say, okay, first I want to evaluate it s equals -2. Now, if I do that using the entire fraction, I'm going to have a problem because I'll be dividing by 0. Okay, so when I do the s equals -2 step, I just ignore this term, right? This is why I call it the thumb method, because you can, you can't see me because I'm not, on the screen, but right now, right, I'm covering up this piece with my thumb. Okay, so there's my thumb, my hand's down below, right? But that's what my thumb looks like. Okay, so you can't really see this. And so now I'm just evaluating the remaining piece when s is equal to -2. And what do I get? 4 times -2 is -8, plus 7 is -1, divided by -2 plus 1, which is -1. Hey, -1 divided by -1. That's exactly what was really going on down here. We had -1 equals -1a, divide by -1. -1 divided by -1 is a. Okay, so my a is 1. Now, how do I get the b? Well, I do the same thing, okay, but now instead of covering up the s plus 2, I cover up the s plus 1. Okay, so here comes the thumb. All right, it blocks out the s plus 1, and I'm going to evaluate at -1, because that's what was going to get rid of this. Okay, at -1, I have -4 plus 7, which is 3, divided by -1 plus 2. Okay, -1 plus 2 is 1. So -3, or rather positive 3 over 1 is 3. And so my b is equal to 3. Now, it is very important to know that this method is not always going to work for partial fraction decompositions. Now, if you have distinct linear factors, you can always do this. No matter how many factors you have, this will always work. Use your thumb, cover up one of the pieces, figure out, okay, what made this 0, right? S equals -1, and plug that in for S everywhere else. So that will always work. If you have repeated linear factors, though, it's only going to work for the highest term. So if we go back to the previous video problem, okay, so this is where Timmy was trying to do a partial fraction decomposition. If we wanted to compute the value of this c, we could use this method. We cover up the s plus 1 cubed, evaluate the remaining piece at s equals -1, and that would actually give us the value of c. It will not, however, give you the values for a and b. As one can check, right? You actually can compute the a and b, you're not getting the same thing. All right. So it will be valuable, but it's not the end, right? You do need to understand ultimately how to do the algebraic version for the more complicated partial fraction decompositions, or decompositions, right, which are going to involve, say, an irreducible quadratic. All right, especially if you're not interested in starting to plug in complex values in for S. Okay, well, hopefully this gives you some food for thought and a few different ways to solve these problems. We'll see you next time.